In the last video, we derived an equation to describe pollution leaving a lake when the rate that water left the lake was constant. In this video, we'll take a look at the same situation but have the rate that the water enters and leaves the lake be a function of time that varies with seasonal rainfall. So let's get into it. As you might have noticed, most regions typically have a rainy season and a dry season. If you live near a lake, you might have noticed that when it's your rainy season, you get a lot more water entering the lake than you do when you're in the dry season. So let's take a look at this graph here. This is the average rainfall near Portland for each month for a 48-month period. And the months are starting in December. So we have a minimum, and 6 months later we have a maximum, which coincides with the rainy season being in winter for this area. This pattern looks a lot like a sinusoidal wave, and that's something we can work with. If we look at the times that the maximums occur, like here and here and here, if we measure the amount of water leaving the lake per month, then we can say that this would be 100% of that flow rate, and then anything in between would be some percentage of that. So about halfway in between, we can say that's about 50%. Because there's 50% less water hitting the ground, we could expect something like 50% less water making it to the lake and leaving the lake compared to the maximum. That way, we could simply take our flow rate, whatever that happens to be at its maximum, and simply multiply that by a sinusoidal function that ranges between 0 and 1, and that represents some percentage of our maximum. So for example, whenever it's a maximum, we'd have 1 multiplied by this, and that's just the flow rate we expect. When the sinusoidal wave is at 50% its height, it's around here, and that's about 50% of the water that's flowing from the maximum. And down here, that's very close to 0. So let's go ahead and just say that's 0. Of course, you might be thinking of other factors like water evaporation, soil absorption, temperature, humidity, and the fact that friction will affect the total flow rate of shallow water more so than it does deep water. We can usually safely neglect some nuances like these and still end up with a pretty accurate model. Remember, in this case, the goal is to make a reasonably accurate prediction, not to try to include every possible contingency that might exist. Because frankly, those types of predictions cannot be modeled very well for long periods of time. Think of the weather forecasts. Those use differential equations to make predictions, but we know those predictions are not accurate for more than about a week. For the level of accuracy that we want, we could simply set up our differential equation in a way that our rate parameter represents a function of time that reasonably represents the change in water flow as we go from season to season. So, we have to ask ourselves, what model will do the trick? Well, we're just getting a gross estimate of what we expect, so we're not going to have to add a bunch of sine functions together to get this exact behavior. We'll just use a single function to represent this. And if we look here at 0, we're roughly at a maximum, so we can say we'll probably use a cosine function to represent this. Now remember, we want to have that function range from 0 to 100%. So from 0 to 1. So you might be thinking we probably need a cosine function that's squared. So that gives us exactly what we want. Now we just need to scale that appropriately so that we get it at a minimum and a maximum every 6 months. Like so. So here we have a maximum at our 0 starting point. The most water is flowing then. And the percentage of water flowing drops until it gets to 0 about mid-year, and then it climbs again until the end of the year. And that's a pretty good model. However, if you recall, we'll probably have to integrate this. In fact, we will have to integrate this. And you might be thinking you need integration by parts. And you're right. Since you probably don't want to do that, we can also use a different type of cosine function where we have cosine. Of course, we need to add something because we can't have it negative. That would mean water is flowing back in from the out port of the water. So let's go ahead. We'll add 1 to that. That gives us a positive. Now we need to appropriately scale it so it ranges between 0 and 1, not between 2 and 0. So we'll just multiply it by 1/2. Okay, now we need to scale it horizontally. So we multiply that by pi and we divide it by 6. And that gives us the exact same curve as we had before through some simple modeling techniques. And that seems to be good enough. We'll just multiply this function r of x that we set up to be multiplied by r, the rate per month, since we're measuring these in months. How are we measuring the volume? Well, we could say that's gallons or something. Gallons per month, or thousands of gallons per month. Whatever it happens to be, we'll go ahead and just use that. As long as the parameter here and the other parameters have the same units, we can use them together. So let's go ahead and set up our differential equation. As you might recall from the last time, we got dP, the change in pollution, divided by dt, the change in time, is equal to r, the rate that water leaves the lake, multiplied by P divided by V, which was our concentration. And then we multiply that by a -1 because it's dropping. In this case, the R, the rate parameter, is no longer a parameter, but a function of time. And that function of time is going to simply be the maximum amount that we get during these months. Whatever that happens to be, we've measured it theoretically. And, multiplied by some function that represents the percentage differences. And that function is just a cosine function of this type. 1/2 times the cosine of pi x divided by 6 plus 1. Let's solve that. And I put together a little bit of music for you just for some fun, so you could watch it animated. You've heard me go through these several times already, and the steps are very similar. So sit back and enjoy a little bit of music I've wrote for you, composed for you, so that you could go ahead and enjoy the math experience. Okay, that was fun. So let's go ahead and now let's assign some values to all this. We got A, which is the initial concentration. Let's arbitrarily say that's 50 grams, 50 whatever liters, whatever we happen to be measuring. Our volume of the lake, let's just say that's 8,000 gallons maybe. And then our rate parameter, let's just say that's 0.7. So we ultimately get the initial value of our pollutant multiplied by e to the -r divided by 2v times x plus 6 over pi times sine of pi x over 6. And in this case, I'm using x because that's the variable in this graph, even though in the derivation we use t. So I don't see that anywhere. So let's go ahead and zoom out and see what we get. Okay, so in fact, we actually do see that we have slowing down and speeding up and slowing down and speeding up. So we could expect this is quite different than if it was just a constant rate, right? If it was just a constant rate, we would not have this sine term here. And we would not have this 1/2 here. Because we would just have the r over v value multiplied by x or t. So this is what we'd expect here if we did not have variation from the seasons. So if there's no rainfall variation, this is the kind of function we'd expect to get And this is the kind of function we actually will get, right? So we can see they're not quite the same. The volume's the same, the rate is the same. The only difference is the rate is always at its maximum. And the initial value that we're starting at with pollution is the same. But we can see as the months go by, that's what we're measuring this in, month after month, we're seeing quite the difference. And we'll get a very big change in how we see the pollution leaving from one version to the other. So there we go. That's how we would model it. In this case, this is a little more realistic if we're expecting rainfall to play a factor in the amount of water that enters and leaves a lake, which makes sense. In this case, by some miracle, the volume leaving the lake is constant every month. And we, of course, expect that to be clean a lot faster. Now, what if instead of having it where the rainfall was determining the amount of water entering and leaving the lake, what if we had some upstream dam that was releasing water where it started for a month and it stopped for a month? So we have a discontinuous function of on and off. How would we solve that? Well, the first thing we'd have to, you know what? That's going to have to wait until next time. Thanks for stopping by. Don't forget to like and subscribe. And don't forget to go to mymerchoutlet.com where you can get tons of great stuff. Again, that's mymerchoutlet.com.